This video is going to give you a quick introduction to how to deal with structures in Matlab, cell arrays and structures. And specifically, we're learning how to load universal file format files or UFF files into Matlab. Before we do that, I'll just show you what is a universal file. Oops. A universal file is a format used in modal analysis. And basically, it's a file format that contains a number of different records. It can store all kinds of data, and it does it with a certain structure. So for example, in this file, we see a record type 58, which is time data. And then there's all kinds of information about when the data was collected, the number of samples, sample rate, the time step, everything is in here. And then the data is stored in this 6 elements per row. This is basically just one column of data here, 6 elements per row. And that will go down until we get to the next record. The next record starts here, and again, the same thing. So it's a strange format. You can't just pull it in Excel very easily. But all of this information that's usually stored in these headers is very valuable. And we can pull that into Matlab in a structured way. So let's look at what that looks like. The call to pull the data in is just this command right here. And notice I don't even give it the name of the file. It'll just prompt me to find the file that I'm going to load in. And I'm going to pick this one. And it reads in the file, and when it's done, it's read in two things, data and dinfo. Dinfo is a structure that has all of these different fields. If I just type that in the command prompt, I can see everything that's in there. Another way to get this is to double click on it. It opens up, and you could double click in further. For example, we can see what these different fields are. So some people like interacting that way. I think it's better to learn how to do it on the command line. So for example, dinfo is a structure which has all of these different fields, and the way you interact with the structure is using the dot. So dinfo period, and then we type something. Also notice if I start to type and I hit tab, it will suggest all of the different things that can terminate it. So you can get through something very easily using that approach. So again, if I take dinfo.error code, I should get back this, which is the data stored in that variable. Right, so dinfo is one variable in Matlab that stores a lot of different data, and it can store it all in a structured way. The main thing that we probably want here is this ds types, which tells us the type of UFF record that we have in each of these things. And basically all of them are 58, which is kind of a response history record. So except the first one, something's funny will be about that one. Right, so we can see the same thing with data, only here it's a little tricky because data is a cell array. So if you're not used to cells, you might try doing this, data parentheses 1, to get the first element out. And notice that didn't help. A cell array needs a special kind of referencing. We have to use the squiggly braces. So the not parentheses, but braces. If we do that, that will let us dive in and see the first field. So notice the first field is a structure, just like what we had above, and it has all of these different fields in it, right? And notice you can mix all kinds of things For example, the units code, I think the 1 is for metric units. The other thing is, so that's a number, but also it can store a name. That's a string, right? And so all of these things get stored in one record. All right, so there's the first field, but there wasn't a lot of interesting stuff there. So we go farther and we look at the second one. The second field, now we see that this starts to have something, right? It says that we have time data of this sensor, that we have a measurement data 4096 by 1 vector of measurement data, and these are the x values that would go with that. So because it's time data, the x value should be time in seconds. And usually there will be unit labels here. This file wasn't saved very well, so it doesn't have them. So we could even know the units. Okay, and in a more complicated data set, this would tell us about the points where these measurements were taken. And so this could be really useful. All right, so there's our data. If you want a fast way to kind of look through and see everything in the data, we can do this. I'll highlight and hit F9. And that little loop goes over k equals 1. There was nothing there, but each time it's printing this field D1, which says what's in there, basically. So we see the first two in this file were time data. The second two were coherence. This third one was time data of the input signal. And then we have a few frequency response functions, right? So if we wanted to get that out, so we already saw that for k equals 2, we could get a time history. And the same thing for k equals 3. So right here, we'll plot that. Here's the x versus mes data, x versus mes data for 2 and 3. So we can create a plot, and right away we can see what it is that we've measured, right? So this is the time response from the 2 accelerometers as the forcing frequency was being swept. And we see that, as we get near this resonance at this point in time, we're getting a really big response. So already we could probably look at this and we could calculate, if we were to calculate the distance, between these peaks, about 0.15 seconds, right? That would give us an idea what the natural frequency was. So 1 over, we have about a 6 hertz resonant frequency right there. All right, so that's the time data. We see in this lab you're interested in frequency response functions. Those are down here. And I don't know why there's 2 copies of them, but let's suppose that we want this one and that one. I think that was just a mistake in saving it. So that's 7 and 9. So here we can plot a frequency response function. And this is plotting those fields and taking the absolute value, because if we look at this, this is going to be complex numbers, right? Real and imaginary part. So that's the complex FRF, which has magnitude and phase. Here's the FRF after we compute, take the absolute value. And we can see our 2 modes if we zoom in here. And we have one natural frequency around 3.5 hertz. And yeah, 3.1 hertz, and another one 6.5. So pretty close to what we estimated from that time series, right? So these are our 2 FRFs. And the sample rate was such that we also collected a lot of signal in areas where we didn't really apply a force. So we get a lot of noise in this area. You know, the transfer function is a ratio of response over force. And if the force is near zero, that will really amplify any noise that we might have. So it's not a worry that that part is noisy. We'll just ignore that. Okay, another thing you can use if you have the tools that were given in class, we could do this. Oops, nope, that's not the one. I can never remember whether it's plot FRF or FRF plot. Yeah, this one will work. So if we wanted to plot that using this function, we could do it this way. Oops. We could type, let's see, I already forgot. We could type FRF plot, and the X vector, it's expecting that to be in Hertz, and I believe it is in this case. That's the default for FRF data. And then we can pass in any data that we want in a matrix. And we pass in the actual FRF data, not just the absolute value as we do with semi-log y. So this will put these two columns of FRF data in, and it will create a plot for us. Oops. And we have a problem because this one gets annoyed if f is a if the frequency vector is not a column. So we can try again. Oops, what happened? So using that function, we get a plot that has the magnitude of the FRF and the phase up here. And that's useful. We can see that the phase goes through 180 degrees, starts at minus 180 and goes through a 180 degree phase shift through the first resonance, and then another one through the second resonance. And so it looks like reasonably good data. One other trick that I'll show you is if we want to zoom both plots at the same time, I created a little function that does that. So we can just click on the region we want to zoom in on. We can zoom multiple times, and when we're done, we just right click. So that zooms both plots simultaneously. All right, so those are some tricks there. We'll learn later that if we've saved the UFF files correctly, they should have response node and reference node data. And when that's the case, we can use loaduff to actually take all of the things out of this data structure and put them in a useful form. So that's what this cell demonstrates. Notice if we do it this way, what we get is an H matrix with two columns of complex data, and get a frequencies vector, a vector of all the frequencies that goes with that. So we can plot that much more easily. Here's the frequency converted to Hertz, the absolute value of the FRF matrix, and then we also get these two structures which have all the name information, which tell us where things were measured. So RSPS, those are the points where the responses were measured, point 1 and point 2 in the x direction. And refs is the point where the force was applied, the input that was used to calculate the FRF. So here we're pretending that that's point 1. And that actually agrees with what was actually done. So anyway, this gives us an easier way to get into our data and to plot it. And so feel free to use that as you go forward. There's another example here where we pull in an even bigger set of data. This one doesn't need any doctoring. and we'll learn more about what's going on here. But this pulls in a 20 by 1 FRF matrix from a kind of a more standard test, and you'll see how all of this, the responses and references will be useful there. Let's just do that real quick, and you can see that. So if we go to the loaduff demo. Okay, so here's some data. So now, if we look at H, it's now a 6,000 frequency lines by 20 measurement points, and actually 2 input points matrix. And in this case, things are flipped, but we have 2 points that are like our references. These are the 2 points here. These are the points where we have the accelerometers in this case. And these are all the points that we measured at. So we measured at points 1 through 20. Notice they're all in the positive z direction. So we could use that to reconstruct what's happening in space. We can correlate those points with where measurements were taking and make sense of everything. All right, so we'll cover some of this other stuff later, but there's an example. So I hope that's helpful as you go into these universal files. It's a pretty easy way to get the data into Matlab.